Hi everyone and welcome. Today we're going to be talking about factoring polynomials. So your goal after watching this video today will be able to factor and understand why factoring works for different types of polynomials. So to start off with our area, so we talked about an example like this to start class the other day in our small groups, and we were saying, okay, so we have the inside measures, and to find the area of this, I'll write this on the bottom here, we would just add them up. But before that, a lot of people were guessing in the groups. Were like, okay, so like if a side length is 12, maybe we have a 4 here and a 3 here. So we were thinking to that second step. And while in class we focused on, and again, apologies for that, we're coming back. So in class, what we focused on with multiplying was getting our area answer, but today we're actually going to be focusing on doing the opposite. So we're not caring as much about the area answer. We are focusing on finding, how do we know these two side lengths here? And then the same thing goes. If we have a side length of 3 here, well, 3 times something has to get us 80, so we need to keep that consistent. And that's actually going to be kind of messy there. We'd have like a 26 2/3 as our side length there. So maybe we don't like that 3 there. Maybe that 3 doesn't work well for us. But again, our goal today is going to be exploring different ways that we can factor some of these more challenging examples and kind of take the area that we know and back it out so we can find some side lengths. So let's start off here, and I want to make sure we got the correct examples to start off. Let's jump in right here. So in our first 3.4 video, we were talking about factoring when we 100% know, what the first and last numbers are. So in this case, again, we still want to make our box. And we still want to fill in that first and last number just like we did before. The only difference is our methods don't work anymore because our first number is a 6. And that leaves us a little bit of a complicated situation here. So we have a 6 for our first number and also a 6 for our last number. So we still want to break out anything that we're factoring into its pieces. So we're going to still want to break out that first 6 into 1 times 6 and 2 times 3. And then the same thing for the last one here. But now it's our job to match up these combinations here, and everything's positive. So it's our job to match up these combinations and see, which one of these have a middle term of 37 when we go through and multiply. So let's try them out. So for example, just some guessing and checking, and this may or may not be right. We're just totally guessing. What if we try a 6 and a 1 x for our first numbers here? And let's see if this works. So maybe if we did a 6 and a 1 for our first example, let's try the other one. Hedge our bet a little bit here. We'll try plugging in, I'll do this one in purple, 2 here and maybe a 3 here. So we get 12x there, we get 3x here. And when we do our diagonal, what we're going to see is that, okay, 12 plus 3 does not equal our middle term. So our like terms don't combine to get the area that we're looking for, so we failed. 2 and 3 don't work. But a good thing to check here is, what if we did it the other way around? What if we did 3 times 2? Maybe this will get us a little bit closer. So what if you had 18 and 2? Okay, better, right? We're closer to 37. We have 20, but still not there. Okay, so it looks like our combination of 6 and 1 for the first term and 2 and 3 for the last term, that's not it. So let's try another combination. Maybe if we try the 1 and the 6. Okay, so let's put the 1 here and the 6 here. 6x, 6x, we get 12. Not great. But again, don't give up on this pair quite yet. Let's try it both ways. What if we did a 6 here? Oops, gotta make sure I'm actually writing and not erasing. So what if we put a 6 here and not a 6 there, but a 1 there? Let's see if this works. 6 times 6 gets us 36. 1 times 1 gets us 1. So 36 plus 1 gets us 37. Awesome. And then 6 times 1 in that last corner does get us positive 6. So this works. So we now know if we factor this one, on our edges we have 6x plus 1 and 1x plus 6. And that is our fully factored out answer. So your goal when you're working through these questions, honestly, is basically to just guess and check. So again, for number 2, we'd make a box. We'd fill in the things that we know, which this doesn't change. So always, 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 no matter what, we have our first number and we have our last number. And then the second thing is always, 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 again, breaking down into our factors of 3 and our factors of 2. And we're going to use these for our edges. So sometimes if you have a number like 2 out front, there's only one option, right? It has to be 1x and it has to be 2x. And the same thing for getting to our negative 3 here. It has to be 1 and it has to be 3, but it's our job. We have to find the correct order of 1 and 3 to get to negative 5. And that's the tricky thing here too, is when you introduce negatives, one of our edges needs to have a negative number. So let's give this a shot here. So if we put negative here and positive here, and let's say, I don't know, let's go with 1 here, and let's see if 3 here works. So we'll get positive 6x, we'll get negative 1x. And when we combine our like terms going across, we get positive 5. So 5 is our number, but we don't like our sign. So if you ever get to that situation where you find the correct number, you matched it up, you're happy, but your sign is incorrect, one minor change is needed. Let's change this to positive and this to negative, and see if flipping those signs helps us out. So positive 1 minus 6, that does get us to negative 5. Let's just double check our last number here. Negative 3 times positive 1 does get us negative 3. So we are happy with this factoring. 2x plus 1 and 1x minus 3. So again, there's no trick to these when your first number is not 1. It's just a little bit of guessing and checking. So again, have those erasers ready. I would definitely want to do these in pen. And just be ready to plug in some different solutions. Now I will have the quadratic formula later, which will help us if we're not sure. But to be honest, even guessing and checking sometimes will be quicker than that. So this is a good way to, again, rely on area, a little bit of guessing and checking, but as long as we're checking those diagonals, we're going to be in good shape for challenging examples like this. So let's actually do a little bit of reverse order today, and let's define what we just did. So we just factored. So we'll write down our definition today as factoring. And factoring is when a number or expression divides a number or expression, I should say another number or expression, evenly. So if we're factoring a number like 36, that's literally what we're doing here, except we're just factoring, instead of numbers, polynomials. We can factor 36 into 6 times 6. We can't factor it into like 7 times, gosh, I don't know what that decimal would be. 36 divided by 7 would be like 5.14 or something. This does not work. That's not a factor because it does not divide evenly. So it's the same thing when we're looking at, factoring an expression like x squared and 3x. We need to find edges of this that factor out evenly. So our factorization here is x times x plus 3. So again, the same idea applies. We need an evenly divisible factor. We're not looking for those messy decimals and repeating things. Again, we're just doing some division. All right, so let's go on to our next example, which is what happens when we have the sum or difference of cubes, so to the third power. Everything we've done so far is to the second power, but what happens when we go to the third power? So specifically, this is what we're going to focus on this unit and this day and this year, is only for cubes. We have sum and difference, and each of those have a different formula. So the sum of cubes, we break that down into a plus b times a squared minus ab plus b squared. And for the difference of cubes, and again, these are good formulas to reference, so definitely make sure you have these in our notes. Just change a couple of signs here, a minus b, a squared plus ab plus b squared. Now I challenge you, if you have the time, to go through and multiply. So go through and do like a 2x3 box once we factor these, and just double check that what we factored actually works, that what we factored gets us to the answers that we have for both of these here. So let's just check in here before we start. We always want to define A, and we want to define B. So we should be a little bit more specific. Each of these is a squared, a to the third plus b to the third. And this is a to the third minus b to the third. So here, a is just x, because a to the third equals x to the third, and b in this case actually equals 5, not 125. because 5 to the third power is 125. So b to the third is 125. So again, if we look at this here, to the third power there works. B to the third power here is 125. So we're taking the cube root of each of these here. So same thing here. A to the third equals 27, x to the third power, but just a, again, cube root 3x. So 3 times 3 times 3 is 27, x times x times x is a to the third. Let's do the same thing for b. In this case, we have b to the third is -1. So just b is also -1, because -1 times -1 is +1. Multiply that again by -1, and we get to -1. So now that we have these, it's time to plug them in carefully into our formula here. So again, a plus b, writing it really small underneath, a squared minus ab plus b squared. So we know that a is x, b is 5, a squared is x to the second minus a times b. Okay, so that's 5x plus b squared is 5 times 5, or 25. For our next one here, we have the difference subtraction problem. So we have a minus b, and then a squared plus ab this time, plus b squared. You'll notice one thing that won't change this term is always, that last one is always plus b squared. All right, so a little bit more challenging, so we have a few more numbers to deal with, but a minus b, so 3x, b is -1. A squared, I'll write this down here to be clear, is 9x squared. 3 times 3 is 9, x times x is x squared, plus a times b. Well, a is 3x, b is -1, so that would be plus -3x. And then our last term, plus b squared. Well, b squared is actually +1, because -1 times -1 is +1. So that would be our final factored answer for each of these. So really your challenge on the sum and difference of cubes is to identify what is a and what is b, and then correctly plug that into these formulas that we have down here on the bottom. So that's honestly, I would say, the hardest part is making sure, like in that second example, that we're factoring 27x to the third into correctly, the cube root of that to get 3x. So that would be a point of emphasis, and other than that, we're more or less just plugging in some numbers here. All right, last few examples. So sums and differences of squares. So we still want to, again, make sure that we are drawing out our boxes with the things that we know. So factoring this out, and again, specifically, difference of squares, x squared minus 49. So we know that x squared is a square, and we know that 49 is the square of 7. But still, let's break this down into our factors. Remember, we are subtracting here. So we have 49 and 1, 7 minus 7. And it looks like we have a 0 term in the middle, so we definitely want to have 7 minus 7 here. So x and 7, x minus 7, checking our work here. Again, diagonals do cancel in this case. So x plus 7 and x minus 7 makes us happy. That's our factored answer. What you're going to notice is you can take squares and it's always going to be plus and minus. So for example, for our second one here, 2y is our first term, and then that's the square of 9, so 2y plus 9 and 2y minus 9. Again, break these down into their squares and then multiply the plus and minus. But let's check this just in case to be sure. That way we know 100%. That's what we're looking at. So let's see if my method of, again, breaking them down into their squares and adding and subtracting works. So 2y, 2y, -9, +9, so we get 18y minus 18y. Our diagonals cancel, and we're happy. So our factorization here works. Our factoring works. So we're going to see all of our squares is going to make us happy. So we can do the same thing here with y, and that would be the square of 1 over 5. In this one here, before we do this one will work. We do need to factor out a 3. And we can do the same thing for 3 times on the outside. And then our factorization of our 2 and our a. So 2 plus a, 2 minus a to help us out there. Again, identify those squares, multiply them with the positive and the negative term. But if you don't trust that, you don't want to do it that way, you can always go back and create your boxes and double check just like we've been doing. One exception though, it only works for the difference of squares. So we do need to be subtracting these. So not going to be the case for here, and let's just double check y. So if we have x and 5 and x and negative 5, you can have x squared, 5x, negative 5x. Okay, so middle terms cancel, we're happy, but there's no way to avoid the fact that that only works for a negative. If we have x plus 5 and x plus 5, we get 10x as our middle term, and that does not work. So this example here, we won't be able to factor it using that plus and minus method. And I just got kicked out here. But we'll finish up. So again, this example on the bottom does not apply. It's not the difference of squares. All right, the final thing to note